In this tutorial, we're going to see how to build machine learning projects and deploy them to production using MLRun. We have several steps. The first step is building a project, which is the container for everything that we're going to do, the models, the code, and so on. The second thing we'll do is data processing and data analysis using built-in or user-defined functions. We're going to train and register models based on the data we generated, run more advanced training using hyperparameter over a distributed cluster environment to distribute the workload and run faster at larger scale. We're going to deploy the models into a real-time serving function. And finally, we're going to see how to automate the entire flow using CI/CD and machine learning pipelines. So the first thing we'll do is import MLRun and create a project. In MLRun, project again hosts the functions, the code, the models, the different data elements, and so on. We create a project. We can save this entire project into a Git or load it as a whole and run CI on top of it. So in this project, we have three different functions for data generation, training, and serving. We use this simple snippet to essentially register all of our code in this project object. Later on, we can use that project object in the CI processes or the automation processes. The first thing that we're going to do in this project is run data processing and log the artifacts that we generated. So we're going to run this piece of code, which is essentially just loading some reference data set from scikit-learn and registering the data set and some other parameters. So those can be used later by other functions that run in the pipeline. So you can see here, we're executing this function. We're just calling something called run function with the name of the function that we registered. We can optionally pass parameters, and we could select where we want to run this function. By default, it will run on the cluster, but we can also select to run the function locally for debug purposes or if we don't want to use cluster level resources. Once we execute the function, it will generate all the outputs of the function. We can go into the MLRun user interface. We can see the different jobs that we're running. For example, this data generation. It has multiple executions. Every time we run it, it will generate a new function. It records all the environmental aspects, the container, the code, which host was running it, and so on. The inputs, no inputs in this case, the outputs, you can even visualize the outputs, the results of the execution, and so on. So in MLRun, you can register, every job can run, can even be triggered on a schedule, and you could do more advanced workflows, as we'll see in a second. So we ran the data generation. We can also run the same thing using CLI commands. Once we execute the function, we have a run object, and this run object allows us to look at the state. Maybe the job is running for a long time, the different outputs. We don't have to use the UI to inspect the different job elements. We also have the data artifacts that are generated by the jobs, could be passed as a pointer or could be even visualized on our client side. Even though the data itself may be stored on some cloud storage or object storage, we can still go and visualize it from our client using the MLRun SDK. The next thing that we want to do is analyze the data set that we just generated using a built-in MLRun marketplace function. So MLRun has a marketplace. In this marketplace, you'll see many different pre-developed functions. We're going to use this one to describe. So you have a full documentation of how to use it, including examples and even the source code. And this function will essentially generate all the different charts and analysis and histograms about our data. In order to run it, we just pass the data that was generated in the previous executions, the label, and if we want to run it locally or on the cluster. In this case, we ran it on the cluster, so it actually generated a Kubernetes pod automatically on the cluster, executed. Although the data was local, you see that it actually managed to pass the data to the function, run it on the cluster, and return all the results. We can also visualize the different artifacts. You can see it has many different artifacts generated with nice histograms, violin charts, and so on. This is the full list of artifacts that were generated by that function. And again, we could visualize some of those artifacts are interactive, which is pretty cool. And you could just use them from the notebook or from the user interface. So once we've done this analysis, now we want to train and build a model. In MLRun, you can essentially write your own training function, but you just need to add a simple single line to your code, which adds all the MLOps. So you see, this is a very simple scikit-learn training function. Everything is normal here. The only thing we've added is something that will automatically log the model, register the model, log the artifact, log the different matrix, and do a lot of other interesting things. So once we've added this line and we're executing this training code that we've just seen here, we can also pass different parameters to it, and it will automatically execute the training function and record all the results in the MLRun database, and you could visualize that in the user interface or directly from the notebook. Look that here we've essentially run it locally inside Jupyter. You can see all those different matrix and artifacts were generated automatically for us. We don't really need to go and log the different results. It automatically knows per framework which artifacts and matrix to log, and those could be used for different comparisons and selecting the best model and so on. So one of the artifacts, for example, that was generated is feature importances, which shows out for every feature that we feed into the model, what is the importance to the final result of the scoring. Now that we ran the training function using a set of parameters, maybe we want to run different sets of parameters. So MLRun, without any additional work, can support many different strategies for hyperparameter tuning. It could also be distributed across multiple containers. So if you want to run many different experiments, you don't have to wait sequentially one after the other. You could just throw all the different experiments at a large cluster, elastic cluster. They will run in parallel. All the results will be collected, and you could even select the best results automatically by specifying the criteria, like in this case, maximum accuracy. So here I'm saying these are the ranges of value that I want to use. It will run distributed. In this case, I do want it to run over the Kubernetes cluster. So in this case, the local will be equal false in case there is Kubernetes attached. And this will generate different pods and different containers on the cluster, run all the different experiments on the cluster, and collect the results. When we'll open the UI, we can see that we can actually compare the different results and even see which result was the best. This is sort of a static table. We also have a nice parallel coordinates plot, interactive, that is generated in the UI and could also be used from the SDK, where we can see which feature, which metric leads to the best accuracy, or any other output metric. So this is a nice widget that is automatically generated for you in case of multiple runs. We can see the output of the hyperparameter run. It's essentially just like the single run, just adds a few more artifacts for the comparisons. When we built the training, MLRun automatically generates models and registers the models along with all of their different metadata in the database. So we can just go to the project and list models, and we'll see all the different models and their matrix. So you can see the comparison. You could use that in the SDK and build different conditions by yourself of how to select the right model that you want to use. Every model is essentially an object. You can see the full details of those objects by using that line. We can also compare the different models or the different iterations of our training just by using .compare, listing the runs and the result set will be compared. And here you can see we can select, how to compare and how to choose the best models. We also have a comparison table that we can use. Now we have a model and we want to deploy that model into a real-time functions that essentially intercepts a request and respond with a prediction answer. You can build very advanced graphs with data processing, pre-processing, post-processing, ensembles, and so on. Learn more about it in the MLRun serving graph link or documentation. Here we'll just use a very simple function, which has an input, has a simple routing function with a single model. In order to do that, we just generate a serving function from our code. It's a very simple code of a serving class with loading the model and predicting. You can also choose that function from the marketplace if you don't want to write your own serving function. We take that function and we add a model, essentially another model to that function. And we can even plot the topology of our serving graph. In order to debug that, we just convert it to a mock server, to a simulator. And with the simulator, we can simulate all the user requests, like getting the list of models from our model serving function, doing inference, essentially inferring the result of the model, providing an input, getting the output, checking the schema of our model so we know which parameters to use as an input and as an output, and so on. There's a fully documented API. It's the same API like other serving frameworks, like Triton or Kubeflow serving. And now that we want to take the function and turn it into a real-time serving function, it runs as a container, the only thing we need to do is deploy function. This will automatically generate containers. It's using the underlying Nucleo real-time serverless engine. It's building the containers, the API gateways, the elasticity, auto-scaling, all of that is built automatically from your code. You can actually see the process. And finally, it generates an API endpoint that could be used by the clients. And we can even invoke that endpoint with some data and get the result to see that the function is actually working. The final thing that we want to do is tie everything we did here in the notebook into a fully automated flow that every time we change data, we change code, we want to build models and deploy the model to production using a workflow. So for that, we need to build a pipeline. In order to build a pipeline, we have a workflow file. The workflow file essentially does the same things we did in the notebook, running the first function for data generation, running the training function, and finally deploying the serving function, where the output of one of the function is fed into as an input to the second and the third, and so on. So here we just tell MLRun, go run this workflow. We can provide some arguments, and then it will just run the different steps of the workflow. It could visualize them in the notebook in Jupyter, get the results, or if you open the user interface, you'll see that the same workflow is tracked automatically, and you could zoom into each step, check the progress as it works, and so on. The same workflow engine can also work using CLI. This is very powerful for integration with CI/CD tools like GitHub Action, Jenkins, and so on. So you can essentially load the entire project from a Git repository or from a local directory and just say, go and execute this workflow on top of that project, and all the outputs of the workflow will automatically be tracked into the CI system. So this allows full integration with all those tools and full automation. MLRun allowed you to take models to production with minimal amount of engineering, minimal efforts in DevOps and automation, and this allows you much faster deployment to production. Check out more about MLRun in the documentation, and specifically the feature store, which is great for building online and offline features, and the model monitoring. Thank you.